All right, so it's 2:30. All right, everybody, good afternoon. I'm pleased to introduce today's speaker, Ian Beckley. So Ian came to this department with a bachelor's in geoscience from Hobart and William Smith College, 2020. When he came here in grad school during the fussy times of the pandemic, he joined John's group where he did his master's degree in Arctic cyclones. After finishing his master's, he moved to my research group where he's doing currently finishing up and working on his PhD. And today he's going to talk about anti-cyclonic absolute vorticity on the equatorward side of jet streaks. The one thing I'll mention is that you can kind of see that his current work is kind of some interesting blend of like Ian thinking with like working in the past with John with like my thinking. So hopefully you'll get to see that as well. So without any further ado, Ian, take it away.
And don't forget Greg Tripoli's influence.
Oh yeah,
Absolutely.
Yeah, from the weather watches. And
All right, testing mic. I can hear myself, so we're good. Okay, well, thank you everybody for coming today. I realize this was supposed to be everybody's Wednesday afternoon off, but I appreciate you coming nonetheless. I figured I'd snatch up that open spot, discuss some of the groundwork that leads to the latter chapters of my dissertation. And so if you read the abstract this morning, you would have seen the word generation in there as well, and I decided I think it's best to sort of leave a little bit for next time and lead everybody to these conclusions. And we'll start out by talking about the persistence of these anti-cyclonic absolute vorticity features that are on the equatorward side of the jet streams. I wanted to start off the talk today with a couple non-work related things because things are kind of weird right now in our field, and my family was in town for Easter this weekend. My folks are up in northern Michigan, and they were without power for about a week and a half due to the big ice storm up there. My sister has lived in Guadalajara, Mexico for like the last 5 years. So it was just fantastic to see them, and it was a nice reminder that there's a little bit more to life than doom-scrolling politics and work, and it's good to spend time with family. Also, plug the Arboretum. The magnolia trees are blooming, and there's a little website you can go to where they post daily updates on what's in bloom. So check it out. And after the talk today, as I understand, there's going to be a discussion of the code of conduct and sort of the department values, as well as an overview of some things going on with NSF and other related funding. So I would encourage you to stop by for that. And I'll try to keep things a little bit on the briefer side so that we get a chance to take a breather between that today. So what are we going to talk about? Well, as I mentioned, I kind of alluded to this, these anti-cyclonic features on the equatorward side of the jets. These are associated with inertial instability, which is something that gets kind of a light breeze in some of our core courses, so we're going to spend a lot of time today trying to demystify that. We're going to talk about this conundrum about the persistence of these features. If we have an instability and the release of the instability wants to remove it, why do we see them persist for so long in analyses? And then if there's some time at the end, I'll go over a little bit of climatology. So, demystifying inertial instability. I find one of the best ways to discuss this is to discuss the analog between it and static instability, which is one that we're much more familiar with. This is the two hydrodynamic instabilities. One, static instability is the need to redistribute heat in the vertical, and inertial instability is the need to redistribute momentum in the horizontal. And the best example I can give of this is an environment like so. You have some isotherms contoured, and in order to know whether or not this lapse rate is super-adiabatic or sub-adiabatic, I need to know something about the height. And so what we tend to do is flip the script into a potential temperature framework, where now if I have a parcel along that top isentrope and I force it down to the surface, you'd find after the adiabatic compression that it's actually warmer than the environment around it. This gives us our statically stable environment, or stable stratification, you may hear me say. However, if I have something like an extremely low albedo asphalt surface and I have some solar insolation that prolongs on that, you end up with these super adiabatic lapse rates in the boundary layer where I have to pack in a bunch of isentropes in that very lowest portion of the boundary layer. This is the mirage that you see driving along the road. It's been tricking people in the deserts for millennia. In this situation, if I immediately turned off the sun or nightfall came, this superadiabatic lapse rate in the boundary layer would immediately need to overturn itself and reestablish the statically stable conditions. So this is how static stability works. The analog comes, instead of now redistributing heat in the vertical, we're going to need to redistribute momentum in the horizontal. And these regions arise when you have extremely strong horizontal shear. So for this example, I have some geostrophic vectors there in black. They're increasing, or it's strong in the middle and it's decreasing along the flanks. So of course there's going to be a corresponding vorticity couplet associated with this. But in order to understand whether or not that feature is inertially unstable, we need to have kind of an analog to potential temperature to determine the stability frame. So what folks tend to use is called the geostrophic absolute momentum, which is basically the geostrophic wind speed plus an adjustment for the Coriolis torque, and it has a kind of a reference latitude y. So if I plug in those geostrophic absolute momentum contours, we now have this new situation. So we'll start with the polar side of this jet, the poleward side, where absolute geostrophic momentum is actually decreasing to the north. And in this situation, let's say we have this parcel A that's sitting along this geostrophic streamline, and it's actually a happy camper. Its pressure gradient force and its Coriolis force are currently balanced. And if someone comes along and gives it a swift kick towards the pole, you would find that upon going to the region with lower wind speed, it's going to encounter a much weaker pressure gradient force. However, we're using parcel theory here, so we're going to state that the parcel will retain its value of absolute geostrophic momentum. And in doing so, this means that the Coriolis torque only changes a little bit. And you'll see that clearly the forces are now imbalanced, and there's a net acceleration that opposes the initial displacement. This is an inertially stable situation, and there's a bit of a clue there in the fact that if you use the right-hand rule on the polar side of this jet, you get cyclonic vorticity, positive vorticity. This is what we might call an inertially stiff regime. On the equatorward side of this jet streak, however, we have a situation where the absolute geostrophic momentum increases poleward. And we can still start out with a happy camper, a geostrophically balanced parcel at A. Pressure gradient force, the Coriolis force are balanced, but if I give that parcel a swift kick, upon reaching its new latitude, it finds an environment that has a much stronger pressure gradient force. The Coriolis force does not increase enough to counterbalance that, and we have a net acceleration that is in the direction of the initial displacement. This is an inertially unstable situation, and this is bad news for the stability of the flow, because as soon as parcel A moves to point B, other parcels need to move in to take its place. And if that whole strip is inertially unstable, you end up with these sort of ribbon-like perturbations that grow in the horizontal and in the vertical. So this is a difference between what we might think of as a global instability. These are things like baroclinic instability, where you have organized transport of warm air poleward and cold air equatorward, or moisture vortex instability, where you have an organized dissolution of the moisture gradient. Instead, we're thinking about these situations where one parcel moving requires others to take their place in sort of a catastrophic overturning process. This is like, think of an orchestra playing in dissonance, completely out of tune. So, there's a couple problems, however, with this absolute geostrophic momentum framework. And namely, it's that we have to pick this reference latitude y. It's also not particularly well suited for curved flows. So at the level of a mesoscale analysis, when you can zoom into a frontal region and choose an x-axis along the front and a y towards the cold air, it works fairly well. But when you get into the curved flow associated with planetary Rossby waves, this starts to fall apart. But we can get some clues as to what the actual criteria for the instability is by taking the meridional derivative of that absolute geostrophic momentum. So if I apply the derivative operator to the right-hand side, you'll see very quickly, if I change the sign of the expression, that we start to have something on the right-hand side that resembles the absolute geostrophic vorticity. And if I did the same procedure on the meridional component, you'd see that that dvdx term that we're missing starts to fall out. So what we're actually looking for in the environment is regions that has negative or anti-cyclonic absolute geostrophic vorticity. And we can come up with a slightly more robust version of this by considering two equations that describe parcel displacements in the horizontal and the vertical. So you see sort of accelerations on the left-hand side, the delta x, the delta z, these are vertical and horizontal displacements. And then you have a Coriolis torque term and some terms that are second derivatives of pressure. And you see kind of quickly that if you start substituting in the geostrophic wind, something like a dpdx term, you can start having derivatives of the geostrophic wind, so horizontal shears and vertical shears. So they look somewhat reminiscent, and these tell us something about the behavior of a perturbed parcel in this flow. And I should point out that this system of equations can be used to solve for both static instability and inertial instability, as well as symmetric instability, which is everything in between. And what we're going to do, though, today is focus on purely horizontal shear. And one of the reasons this works well is because when you get to the limit of a very, very strong horizontal jet, you start to dominate the relative vorticity starts to dominate over the horizontal vorticity. So the relative vorticity dominates over the horizontal, and we can approximate this with just purely horizontal shear. You start having solutions that look like a displacement on the left-hand side, a delta x and a delta z, which is equal to an initial displacement, a capital X, capital Z, and then a growth term, an e to the I omega t, where omega I is this inertial frequency. And sort of classic instability theory, if omega sub I is positive, the initial parcel displacement will come back to its original location with a little bit of an oscillation along the way, but it ends up being stable. If we have I omega end up being negative, now we have the catastrophic overturning scenario where the parcel is accelerating away from its initial location. And you see that this results in a hemispheric independent result, which is kind of handy if you're going to do like a global climatology of one of these, of this criterion. In the northern hemisphere, F is positive, so we're looking for regions of negative absolute vorticity or anti-cyclonic absolute vorticity, and then flip those signs in the southern hemisphere. So where would we look for one of these phenomenon? Well, the go-to location is an upper level jet stream. And so this is a 400 hectopascal map of isohypses in the black. These are the geostrophic streamlines, and then the isotachs shaded in the blues. And it might be tough to see, but at the center of that jet streak, we're pushing into the 80, 90 meters per second range, which is about like 160, 180 knot jet. It's pretty fast. This would be a quick trip from Anchorage down to Dallas. If I throw some geostrophic vectors on there, you get an image that starts to look a lot like the model we showed earlier on in the talk. And so you have a cyclonic portion using the right-hand rule on the poleward side of this, and an anti-cyclonic portion on the equatorward side. And if I actually calculate those relative vorticities for you, we end up with the classic vorticity couplet where the sort of white streamline in between is the jet core. The problem here is, though, we still need to add F. We still need to add that planetary vorticity component. And so at 35 degrees north, it's right around -9 times 10 to the -5th. We add that on, and you see we back out this little sliver of anti-cyclonic absolute vorticity that's on the equatorward side of the jet. And I will note, this is a feature that often does not get plotted on standard maps of absolute vorticity. And hopefully by the end of this talk, you'll start plotting those values on your maps. So we'll cut a cross-section through this feature for a little bit of an extra peek at it. In this image, you have pressure on the y-axis decreasing with height, and you have isotropes colored in the sort of light gray color. You have the dynamic tropopause in black, which delineates the stratospheric and the tropospheric air. And then you have the isotachs colored as they were before. This gives you the idea that in the subtropical air, the tropopause is quite high. In the polar air, the tropopause is quite low, and that the jet typically relies sort of on the change between the subtropical and the polar air mass, where that dynamic tropopause is steeply sloped. And this is a classic sort of tropopause fold, and it's actually a similar event to one that John investigated in his 2014 paper. So if you're more interested in it, I'd refer you there. Again, if you remember that this jet is flowing out of the board in this situation, you can use the right-hand rule to back out the relative vorticities. I've done it for you and added that planetary component to show you this little tube of anti-cyclonic absolute vorticity that's on the equatorward side of this jet stream. And this is solidly in the middle troposphere of the subtropical air. This is also a nice illustration of why it's useful to do analyses of these features at different isobaric levels, because if you did a 250 hectopascal layer, you would miss this event. Okay, so what does it actually mean to release the instability? So we have this anti-cyclonic absolute vorticity feature. That doesn't necessarily guarantee you the release of instability. And the first step that you kind of need here is the kick. You need something to perturb the flow in that location. And if you run this in an idealized simulation, there's been some papers, Thompson and Schultz provide a relatively nice one, example of this. And they don't give an initial perturbation. It actually takes several days for the perturbations to begin to grow. I'd like to think that nature would provide this for you at an earlier time, but I think the jury's still out. This is important observational work that still needs to be done in this area. So if you perturb the flow, we have the growth, the solutions to those equations. It was a displacement on the left-hand side times an exponential growth, e to the I omega t. And so what will happen is you have these horizontal and vertical velocity perturbations that grow in time and space, and this notably can release or can result in clearer turbulence, which we'll talk about a little more in a second. And sometimes there's a bit of a disagreement in the field whether or not the perturbations associated with the instability are also inertia gravity waves. Some differentiate between the two, others don't. My work is not necessarily trying to get into that argument, but I think more observational evidence is needed. But what I'll point out again, the goal here is to mix momentum laterally. So upon kicking, the perturbing the flow, we should have these horizontal and vertical momentum. The growth of these disturbances should spread momentum laterally along the isotropes. We're trying to decrease the horizontal shear. Eventually, upon doing so, we should see this feature disappear if those were doing their job. So in idealized simulation, Thompson and Schultz show what this might look like. They initialize a jet somewhere around 11 kilometers, so much higher in the troposphere than we were showing previously. It takes some time for that perturbation to develop because they didn't provide a seed perturbation to begin with. But once they develop, you get these fairly robust perturbations of meridional wind on the order of a couple meters per second. I believe the maximum values were around 7 meters per second. And then at the same time, you have these vertical motion perturbations, something on the order of a couple centimeters per second. While this might not be the strongest clearer turbulence that you could encounter, I would not serve dinner while flying through one of these regions. You would want to have the seatbelt sign on. And so the Thompson and Schultz paper, they calculate for a couple cases, a couple sample cases, and they basically find that they're associated with light to moderate clearer turbulence. So a couple reasons why these features are important. Again, as we alluded to, they could be associated with clearer turbulence. Another one, and this is a growing body of work that's looking at this, is the association to downstream model errors. So this is a big one. Basically, you see growth of root mean square error, height fields and wind fields at the upper levels, upper tropospheric levels, when you have this phenomenon occur. And this is both because of the actual injection of the negative absolute vorticity, but it's also the fact that the models can't necessarily properly simulate the release of this instability in the first place. And it's a growing body of work that's showing this related to mid-latitude cyclones, tropical cyclones, and even just tropical convection from the Hadley cell. So it's a super interesting area of work. Another one that I want to mention for people who may be more on the mesoscale forecasting side of things, these are really, really nice areas to, inject your outflow if you're a tropical, or if you're a convective system. And the reason for this is this sort of just simplified version of the vorticity equation. You have a tendency in the vorticity on the left-hand side is equal to a divergence term that's scaled by the absolute vorticity. So if the absolute vorticity happens to be 0, you don't get the anti-cyclonic tendency of your outflow, and so you end up increasing your deformation radius, and it's really, really easy to evacuate your outflow from this convective system. So that's another reason why you might care about this on sort of a forecasting time scale. Okay, so what I want to hit really hard today is this idea of the persistence conundrum. This is the idea that if you're an avid reader of Holton's textbook, which I'm sure everybody is, he has a section on inertial instability, and it has a pretty strong claim that these regions on synoptic scales should be necessarily short-lived. And this is because as soon as you have anti-cyclonic absolute vorticity, it's supposed that the perturbations are then released, and the instability is sort of self-removed. And this is kind of in conflict with some recent investigations. You have observations from the far western Pacific that indicate that the subtropical jet has these regions for something like 30% of the winter time. You have the modeling results of Thompson and Schultz that show that these perturbations can last for days at a time. And what we're going to show today is more of a theoretical approach about why we suspect they persist for so long. And again, I'll just remind everybody, the idea here is that the release of the perturbations will spread momentum laterally, and then thereby decreasing the horizontal shear and drive away this green region, this bluish-green region of anti-cyclonic absolute vorticity. So the release of the instability should remove itself in time. So what we're going to do first is we're just going to click through an example case from April 2013 using some JRA data and just get an idea for how long these things last. So here's kind of a sample of what I'm going to show you. These are at the 400 hectopascal level. You have isohypses in the black, you have isentropes in the dashed blue, and you have the absolute vorticity shown in the shading there. And this is at 0Z on the 8th of April. One thing I'll note, we do a little bit of smoothing to the isentropes and the isohypses just to make it a little cleaner, but we don't want to smooth the absolute vorticity field at all because linear features respond really, really strongly to smoothing, so we want to be really careful with that. So I'm going to expand your view a little bit. So this was the feature we were showing. Again, isohypses in the black, isotherms in the blue, and absolute geostrophic vorticity. And you see that there's this little speck that's just originated on the equatorward side of this strong jet streak. So you have very strong geostrophic winds in that region, and you have an anticyclonic vorticity feature on the equatorward side. As we click forward in time, this trough begins to develop. It starts to dig towards Southern California. It ends up kind of cutting off, at least loosely cutting off from the upper level flow. And this feature has not only grown, but it's persisting for several analysis periods. So we're now at 12Z on the 10th, almost 2 days later, 0Z on the 11th. Starts to wane a little bit there on 12Z on the 11th, but we get another peak of it at 0Z on the 12th. So this feature's persisting for almost 4 days. And I would say that flies in the face of the expectation that they're short-lived. I mean, 4 days is a prolonged phenomenon. It's pushing onto the synoptic scale. There it finally disappears there on the 6th. So we get about 4 days. Okay, so the conundrum here. We discussed the fact that this inertial instability is persisting in the environment over several days. However, we should expect that the unstable perturbations that would arise there would mix out that feature. At least that's the existing theory. But what we're going to do is do a little bit of a timescale analysis here. So what I have here is the E-folding timescale for the growth of these unstable perturbations. So you remember it was a delta x, the displacement growing like e to the I omega t. Well, omega was the inertial frequency, so it's 1 over the square root of that inertial frequency is going to give us a time scale for the development of these features. And if we make some assumptions about the values on the denominator there, we have that the absolute vorticity is a small residual from the relative plus f. So f at something like 45 degrees north is 1 times 10 to the negative fourth. In order to get negative absolute vorticity, I need to have a value of at least that magnitude. And the summation of those could result in something like an absolute vorticity on 1 times 10 to the negative fifth. This will give you a square root of 1 times 10 to the negative ninth in the bottom, which comes out to be something like 9 hours. So it takes 9 hours for an unstable perturbation associated with the release of inertial instability to develop even by an order of, by a factor of e, which is only like 2.71. It's not even really that much. Now, let's compare this to the time it takes for a parcel to actually flow through our jet stream. So we're going to pretend that we have a geostrophic parcel that's flowing along this isohyps here, and it enters the region of anti-cyclonic absolute vorticity and then exits it. How much time will the parcel actually spend in that region? And if you kind of make some assumptions about what the advective time scale is, something like a length scale divided by the wind speed, we see that that only comes out to be about 6 hours. So the parcel is spending less time in the jet than it takes for the perturbations to actually develop. This is pretty interesting. So just reiterating that, 9 hours in this weakly unstable condition versus a 6-hour time scale inside the jet. So I have another way of sort of depicting this for you. I have the y-axis is the time scale, and then the x-axis is latitude. So I'm plotting the e-folding time scale for inertial instability as a function of latitude. And you see that in the tropics, in the deep tropics, and into the subtropics, this time scale is something like a little over a day to about half a day. And then as you push into the mid-latitudes, you start to approach about 6 hours. Again, this is the time it takes for the perturbations to develop by a factor of like 2.7. Now I'm going to plot some lines that are actually constant with latitude. They're just advective timescales at different wind speeds. So here's a 25 meter per second jet, a 50 meter per second jet, and just for fun, an 100 meter per second jet, which is maybe a little fast, but illustrative. It's very clear that for the 25 meter per second case, there's this huge region in the deep tropics and in the subtropics where those timescales are just not matching up. And if you increase the wind speed, that inequality grows across the domain. So the idea here is that basically in the subtropics, you can have tons of these events, and they can be very long-lived, because as long as they're flowing through a jet stream, they're not really experiencing the instability for long enough to grow the perturbations. As you push into the mid-latitudes, you can still have that phenomenon occur, but the threshold wind speed value starts to increase. You need to have a faster jet to assure that that's occurring. So what are we going to do? We're going to try calculating these timescales for this case. So this was the initial time period at 6Z on the 8th. We have a inertial timescale, an e-folding timescale. We're going to calculate using F and the geostrophic relative vorticity. This is going to require us to do a little bit of smoothing because we don't want to divide by 0. And then at the bottom here, we're going to give it a length scale of about 1,000 kilometers, and we're going to use the wind speeds from the data. So I'm just changing the view a little bit here. You have your isohypses in the light gray, because I want to sort of push them into the background, and then I have that anti-cyclonic absolute vorticity structure with just the dashed black line, so hopefully you can spot that. And what I'm going to do now is plot in red everywhere on the map where the e-folding timescale is greater than the advective timescale. And it happens to be in the exact location that our anti-cyclonic absolute vorticity feature is. And as I step forward in time, it's pretty consistent. So the idea here is that we used to think that these regions of inertial instability would be essentially self-removing. And the argument here is that parcels are actually flowing through that region faster than the perturbations can grow, and therefore they can be quite long-lived, and we should actually expect them to be persistent features. It also alludes, perhaps, that the genesis and the end of the event, how does this actually leave the flow, might not necessarily be tied to the release of instability at all. And it might just be the evolution of the flow into a different state on a large-scale view. And that's sort of the theme of some of the ongoing investigations. Cool. I would say that concludes the first chunk of the talk. So if there's questions about this theoretical aspect, I'd love to take them now, because we're going to move into a more climatological perspective next.
Yeah, this is great, especially for what I'm doing. And I have a question. So your weekly unstable perturbation, the one that goes equatorward, you show the map at the 400 hectopascal levels. Have you seen how much it stretches down in the atmosphere?
So you're talking about the red region here?
The green region that you have in the
Oh, yeah.
geostrophic absolute.
Yeah, so maybe the best is to go back to the cross-section.
Yeah.
And give this one.
Yep, perfect, that's,
So, yeah, the bottom looks to be somewhere around 600 hectopascals up to just above 300 hectopascals. And as we'll go into in the climatology perspective, it's often really nice to look at that in an isotropic perspective. So, but for some of the end users, I think they probably do prefer hectopascals, some of the pilots and whatnot.
yeah, well, they do everything 5 mils, that's another story. And the other thing is like, do you know specifically for this day, I'm just having like ideas right now,
Sure.
for example, if we wanted to look at PIREPs and talk to you about this, do you know what specific date is this case?
This is, this would be the 8th of April in 2013. Yeah, John?
Yeah, Ian, am I off track here in imagining that, you know, the idea that you've got a region that meets a threshold condition for instability, and therefore if it's perturbed, you might release the instability and thereby bring your condition, your background condition back to something that's more neutral. That's all true so long as there's no forcing for continued production of the instability, right? And in this case, you've got a strong upper level front developing, and it's tilting vertical shear into horizontal shear. And it's doing it in such a way as to keep replenishing that region of negative absolute vorticity. So I think that the expectation that one reads about in Holton and Hakam about when you have the instability and if it's perturbed, you'll get rid of it, that's all well and good, but only if there's no continued forcing for reestablishing it. And that's what I think I'm a little bit lost on. And maybe you're going to tell us in the second half, I don't know.
Well, I agree. I think that actually alludes maybe more to what I was hoping to talk to in the future, but what John's getting at here is that, so in this middle panel you have vectors that represent the horizontal vorticity. So you're facing the jet, and the jet's at your back and the wind's going with you, and you put your hand up in the air and you do the right hand rule. You get a horizontal vorticity vector that looks like this. And then I have a strong gradient in vertical motion there at the top in the black lines, and so I literally just push this vortex tube down and angle it into the vertical. So that's, I think, what John's alluded to there, the tilting mechanism, and I've actually contoured it blue here. So you have parcels flowing along in isohips, it runs into this tilting region, and it's being strongly tilted into the vertical. This is producing the region of anti-cyclonic absolute vorticity. And I think it's both, John. I think there's a consistent production mechanism in this tilting mechanism, and I think it's also being removed by the oppositely signed tilting mechanism on the other side. And so the persistence of the region is probably both to do with the production mechanism and also, I think, to do with this theoretical perspective I presented.
Does the production make it so that the time scale for the parcels moving through it is too short? Or is that somewhat independent? And we need to talk about this offline. I don't want to slow down your talk.
So it's okay. I think it's a good question. I think the spatial scale of the jet matters a lot.
Okay.
The spatial scale of this tilting pattern will set the scale of the absolute vorticity feature, which is that purple that's in between.
Okay.
So I think I agree.
So I like your comparison of the two time scales, but I'm reminded in the middle atmosphere community in the 80s when we talked about inertial instability in the tropical middle atmosphere, that we realized they're linear growth rates, and they're very small. The time scales are very long. I think if you analyze like dWdt and dVdt, you get a shorter time scale, integrating those two equations explicitly somehow. This is a linear result, square root of f zeta. And I want to also point out the idea of persistent source, which is, in this particular case, is there a chronic region of convection associated with this trough?
It's a good question, and what I would like to allude to in the future is that there are cases where you actually have the production mechanism occurring in a region of large-scale descent. That's synoptic scale descent, and I think that would suppress convection. It's actually what I would call one of my dry cases. Then you have the situation that's my other paper, which is about the extremely other end of the spectrum, where you actually have a tropical cyclone that's injecting these parcels into the upper troposphere, and that's something I'd like to discuss next time.
What is the contour interval for omega in the previous plot?
In the previous plot, the contour interval for omega is 2 decapascals. So it's
Yeah,
about-
what decapascal is what?
About a couple centimeters per second.
Okay.
About, I believe that's right.
Yeah, it's about a
So I
microwatt
think
per
those
second.
numbers are on the order of 10 to the minus 5 per second per day then, for production rate,
Yeah, I think that's actually correct.
which is long, and that's consistent with the linear idea of a growth rate. But it's really long compared to the advection time scale.
Indeed.
Hopefully, maybe final question. So I'm curious, when you're doing this, you're using geostrophic momentum, but clearly it's in a jet streak and, you know, there's a lot of ageostrophic motion. If you use something like a semi-geostrophic perspective, how would that change your perspective on what's going on? So if it wasn't just the geostrophic winds involved in advection.
That's a good question. Not sure that I haven't actually done that analysis to state that for a matter of fact. I mean, one of the things that makes me think of is the sort of feedback mechanism in the semi-geostrophic equations, where you have the ageostrophic convergence actually feeding back onto the vortex stretching term. So that would probably change a little bit about what happens on the right hand, the first term on the right hand side there, by adding that ageostrophic convergence. But what I would say though is that using the instability criteria and the theory arises from the geostrophic equations, and so it seems like it's been a safer bet to use that geostrophic perspective. That's why I've used it. Evan?
If you're interested in whether or not your persistence of this is due to a continuous source term or due to the particles flowing through the region, would it be, this is epic, I don't know that much about this, but could you look towards the end of an event like this, specifically when you know the source term is cut off, and then see how long it takes to dissipate at that time, because then you're trying to isolate one possible effect from the other?
Yeah, I think that's a fantastic question, and it's something that is being worked on for this paper. One of the things that I will point out that I didn't necessarily allude to is, let's go to the actual map. So we have this situation right here. This is kind of at the end of the life cycle of the cutoff low. So the cutoff low is starting to rejoin the mid-latitude flow. And that the advected timescale L over U works really, really well when the feature is quasi-stationary, but it doesn't work as well when the feature is moving along with the flow, because it drastically changes your denominator, that U in the bottom. So I think you're onto something there, where like, once this feature is, it's a twofold process. You cut off your production mechanism. Now the inertial instability might be able to do some of its own work. But as this feature rejoins the flow, the advective timescale starts to rapidly decrease because the denominator decreases, and so other way around, right? But and so the feature rejoins the flow, and I think that imbalance changes really fast. All of a sudden, the parcel residence time becomes much stronger in that jet feature, and the instability can work on those parcels more. Maybe that's a good question. Cool. Thank you so much for the good questions. All right, so I'll just go a little bit longer since we have a little bit of time. Talk about some of the climatological aspects of this work. And what I'll note is that there are existing climatologies. So there is an existing climatology from Dave Schultz's group back in 2018. It's well done. It's a robust paper. But one of the things that I do draw issue with is their mandatory use of the 250 hectopascal layer. We showed that earlier. We cut the cross section through our feature, and it didn't even reach 250 hectopascals. So they're missing events. And what I'd like to allude to is some fantastic work from Libby Orr in John's group, where she's actually identified the wind speed maximum in different isentropic layers. So this is the y-axis is each isentropic layer, and then on the y-axis is the frequency of occurrence of the maximum in wind speed along that jet. And by doing so, they backed out the basically trimodal distribution of the wind speed and then in the mid-latitudes, you have a polar jet that likes to live somewhere around 320 Kelvin, a subtropical jet that likes to live at 350 Kelvin, and then a polar night jet, something around 415 Kelvin. And they have this really, really nice table that tells you at every month where would you find that jet in isotropic space. And in my humble opinion, this is probably the way that we should move when we're doing climatologies of upper tropospheric phenomenon that have to do with the jets, because you can actually get it right. So we're going to use these values from the tables to calculate the inertial instability criteria from at every grid point on the JRA 3/4 of a century analysis from 1979. And I ask, does the grid point have inertial instability, yes or no? We're going to break into warm and cold seasons. This was a big, important finding of Libby's thesis, was that in the summertime, the jets kind of become unimodal. So you have to be very, very specific about the isotropic layers that you use and what times of the years you use them. We'll take the time mean, and then we'll also throw on the sort of climatological location of the jet. And we end up with a distribution that looks like this, and I realize the contrast is tough. I've been trying to figure out the best way to do this visualization. The blue line is the climatological location of the jet core. It's called the core isotel, but for all intents and purposes, this is the climatological location of the cold season polar jet. And you have these various regions where you have more time with, basically with inertial instability in the domain. And what I've done is I've calculated this by averaging around every latitude line and then subtracting the mean out. So you get, that way I'm able to actually highlight the regions so you're not trying to differentiate between the grays. So on this panel B here over with the polar jet in the cold season, everywhere where you see red, you see more of these events than you do on other locations on that latitude line. And anywhere you see blue, you see less events than you do at other locations on the latitude line. And you can do the same thing for the unimodal jet in the warm season. And there's a couple of regions of interest that pop out to me, mainly this one that lies basically coming off the Himalaya mountains and then extending. These are potentially even two separate areas, but extending well into the Central Pacific, somewhat reminiscent of the mid-latitude storm track. And then another one that comes up the coast of the United States and into the North Atlantic. It's much stronger in the cold season towards the Atlantic side.
Are those two lower plumes just crossing the equator?
It only goes to 15
0?
degrees north.
Oh, okay.
So this might help. I've also done this for the subtropical jet and trying to use in the boreal cold season, and then they don't have results for the southern hemisphere yet, but it was pretty safe to just use the winter months. And I can do the same zonal averaging and take the means and subtract them out. Notice that there's a bit of change in the contour intervals there because it's much more common in the subtropics and in the deep tropics. And now you get a perspective from the equatorial. And I think it's really interesting to talk about what happens here in the tropics, but sort of on the theme of the talk here, we're thinking more about what happens on the equatorward side of the jet, which is this heavy black line. And one that pops out to me is this region just north of Japan and then moving a little bit southward in the southern hemisphere. And that's a region that is likely tied to the outflow from the Hadley cell. I think that's established in the literature. So that's the climatological perspective. I haven't figured out how to fit all that into the papers yet, but I'm working on that right now. Next time, stay tuned for production mechanisms. We're going to have a little production palooza, talk about how these things arise. Thank you so much. And I'll take some more questions.
Boreal cold season, December, January, February. What's the mean
So-
for that? I'm just looking at the negative signal that we have off the coast of Africa.
Yeah, so I actually define that relative to Libby's climatology of the jet. So the cold season is any time that the jet is not unimodal. So it's from January to April, and then from November November through April. But you have to remember that April and November are the changeover months.
Yeah,
So there's
so you have that
substantial change there.
Yeah.
John?
One obvious thing that interests me from your last plot is what if you start looking at periods of fairly frequent puddles of inertial instability at jet level in that region of red, and then look at periods of time where in the same location it's not particularly active that way. And then is there a difference in downstream predictability in both in time and space? Is there a difference in jet structure that evolves and so on? That could be really, really interesting. How's it connected to MJO? A lot of things you could probably look at that way.
Yeah.
Because that is an interesting spot.
I did try to back out the MJO signal. Victor helped me with this recently, and I had a lot of trouble with it, trying to look for kinks in the subtropical jet with the MJO. I think something that could be interesting is that little region that's just south of Japan, off the coast of Asia, to do like a EOF analysis or something like that of these events in that location. So,
Because that's a place where you can have convectively driven production of these features, and it probably is the only way that it's done. And they can last a long time, you know, and they migrate. They become these big anticyclones at the tropopause level. They can migrate along the jet and upset all kinds of things downstream. It's really interesting. They're a real menace, and I think they haven't been investigated very much.
cool.
Have you considered looking at this in terms of what would be the impact of ENSO on non-ENSO years?
I have not. I think that could be pretty interesting, especially for this plot. Maybe you see less reds in the top plot in certain years and more in others.
When wind blows around a sailboat sail, can shears generate inertial instability?
It's a good question. I don't think that flows geostrophic.
Sorry, I'm just. Okay.
Can I ask one other question, Ian?
Yeah, Evan's got one.
Oh, sorry.
Yeah, this is just a quick question.
Sure.
It would be cool to see some of the stuff in the southern hemisphere. I think just because you might be able to get more clean examples where you don't have to worry about like differences in the jet depending on the where you are, and yeah, I don't know. It just seems like a better test case for these sorts of things. I don't know if there would be anything different going on necessarily.
Yeah, I have sort of like what I've done down here. It looks like I forgot to change that to B. That's a nice tip. But I've done like sort of the summertime perspective as well for the southern hemisphere, and you're right, it is interesting. It tends to be much more symmetrical. That's my sort of analysis of it. And they tend to, it seems to like really like the mid-latitude storm tracks, and then there's sort of this devoid region before you get something interesting going on in the tropics. So I think that's totally true. You might be able to take away some of the effects of the terrain that might be, like, for example, you would have noticed in this plot, like something's going on with the wind. It's disturbing things for sure.
Yeah, 1.4 PBU is probably at 600 millibars or 500 millibars or something like that. So that's running right into the mountains.
The Sherpas are quite literally walking through that.
Right.
I thought in my last 4 papers I'd figured this out, but you're right. There's a lot of room for understanding this more, especially the point that, I mean, when we first started talking about this in 2013, I was saying, look, at 500 millibars, there are these amazing streaks, and everybody's going, what are you talking about? But they're there, as you see. I think you're right that the answer isn't known because it does, the larger scale features are large at 500, not at the tops of thunderstorms. And so the QG perspective can be helpful. I just want to encourage you to also check the omega and W fields with integrated, numerical model output. They'll have similar values, but then you can also say, we don't know exactly what gave rise to that vertical motion field in the numerical model. And then there's this QG version. They'll both be similar, and they'll give clues as to the cause. I mean, there's differences in radiative heating inside the polar air and outside that could make a difference. and then the net effect of all the thunderstorms on the equatorward side of the jet might be relevant, but I think you're finding something that's probably legit.
I think that's true. I think it would help me close my vorticity budgets using the full vertical motion from some of the model output.
Well, and as a proxy to that, because I really agree with that, Matt, and Matt's done some great work on this problem, and it's just neat that this is another perspective that adds to it. On the April 10th, 11th timeframe, 2013, when your upper front feature has kind of rounded the base of the trough, and then you still have these little regions of negative absolute vorticity. Is there a squall line out there in the Great Plains? Because
Yeah.
it looks like it.
I should check that.
And so I got a feeling that there's a life cycle story here that's really more interesting than we might already know, which is one there's an adiabatic part of the life cycle that initiates these things, and that's the upper frontogenesis, related to the upper frontogenesis process. And then when it comes around the base of the trough, it's the convective one, where you got updrafts that are splitting vortices, and you're maintaining a line on the anti-cyclonic shear side of that. And it's, convectively unstable boundary layer area that finds itself in a region where the stability is positive at 500 millibars. The only way it can conserve PV is to become inertially unstable.
Right.
And so there's a dry adiabatic part of the life cycle, and then there's a convective part of the life cycle. And whether or not that's consistent through the CLIMO would be really, really interesting to find out. So there's a lot of good stuff, yeah.
Thank you.
One last question, just to get some time through.
Yeah,
absolutely.
I honestly was thinking about this within the context of transport too, global transport. So you said 1.4 PBU, you're estimating that to be what, close to more 800?
No, it's only that low in the mountainous regions.
I was looking more into I looked at that spot that you have right next to the coast of Africa and the seasons
Sure.
that you were talking about. For me, immediately I was thinking about the circulation and the dust transport in there that's triggered
sure.
by also
Sure.
by the presence of jets in Jet Street. So I was kind of wondering because it looks very, very similar to the climatology of Saharan coast.
Oh, interesting.
Yep. You saw the hotspot there.
It's nice to see a resurgence appropriately for go inertial instability.
Yeah.
People ignored it for a
I
long
know,
time.
yeah, I
So,
know,
no.
I know.
Cool. Thanks, everybody. Appreciate it.
All right.